So what we discussed was basically we started with a simple example. We say we have two categories of fruits, like apple and banana. Then we talked about using different measures or features from these two classes to design our classifier. So 1, 2, 3, 4 was the apple, class was A, and B is banana. So we used weight. We realized that weight is not a good feature to classify these two classes. As we saw here in this figure, we saw that the distribution of the two classes over the weight feature is very close, no distinction between two classes. Then we talked about using lengths, and by the lengths we had the this concept here that we fit a rectangle over the image of apple and banana, and the length of that rectangle is used. Then we realized that if the green is the apple and this one is the banana, we have a threshold. Maybe there is a little overlap in here, but we have a threshold that with a high enough accuracy, we can use that single feature to classify the two classes. So this showed the importance of the feature selection. Also, we talked about problems like this in which one single feature is not enough for classifying the two classes, like this one. You cannot put any specific threshold in here. For example, you cannot say, I will go with anything beyond this line or any other line. So we have complicated boundaries between two classes. So we need some classifiers that are beyond some specific thresholds in single feature, or much more complex than a single line or a single plane, like a book. We say anything to the right of this phone, anything to the right is apple, and anything to the left is banana if we have 3 dimensions. So this was just opening the problem. We mentioned that there are different phases, steps to our classification problem. One step is the feature extraction. Using different examples, and as we will see again, we talked about the importance of feature extraction. And then also we talked about feature selection, which is another step, usually after feature extraction, but it can be included in the feature extraction. So feature selection is a specific case of feature extraction, but this is so important that we give it a different, distinct name. Also, we have other terms like classification rule and also the classifier and the error of the classifier. So we talked about feature extraction. For feature extraction, we say if we want to separate apples and banana, assuming apples are red apples and banana is yellow, we used Microsoft Paint to see what is RGB, red, green, blue, of the red, and what is RGB of the yellow color. RGB of the yellow color is usually, it is combination of red and green without blue channel. So as you see, compared to the red one, which is having high value for red channel and nothing for blue and green. So as you see, even using the simple green, we can separate. If we have a sensor reading 3 channels of RGB, if we want to separate 2 classes, that one is red and another is yellow, we can use the green channel simply. Anything that has low green would be red in our case, and if it is above threshold, it will be yellow. Also, This one was a simple example, but we talked about much more complicated cases. For example, for face detection. So face detection is not just feeding the photo or image of the person to the algorithm and expect the algorithm to recognize the person. We need to help the algorithm to focus on some points of these features that are important. Because, for example, if you see my face in here, so I am in the middle of the screen at this point. If I move to the right, I am the same person, but the image, if you compare these two images, they are totally different images. So we need to help the algorithm to understand, for example, make the image shift invariant. We need to teach the algorithm that if you see an ellipse in here, find first the ellipse and focus on that ellipse regardless of the position of the image in the screen. And if you find that big ellipse, then focus there. Find, for example, the nose by fitting a rectangle, a triangle on the nose, and also find the eyes, maybe this eyebrow and lips, eyes, and then use those features to create the geometry of the face. So it is really hard because we can easily say this is person one, this is person two, without thinking how we recognize it. But we need to think of why this person is different from the other person. Is there any difference in the geometry? What are the main important characteristics that differentiate people? So we need to help the algorithm by feature extraction. Usually we have raw data. We apply feature extraction to get to some features that we believe they are separating two classes. We are not sure. And also, one thing makes this process complicated, and that is that let me see how I can explain it. So sometimes two features, okay, might not be able to separate two classes individually. But those two features together can separate two classes with 100% accuracy. So it's not always the case that the best individual features are the best features in our classification. They are candidate, they are our first guess, but sometimes there are examples like this one. Let's see one example in here. These two features, individually, they are worthless. Let's see this example. I have two features. For example, one is F1, or let's use X1. Feature 1 is X1 and feature 2 is X2. And let's assume this case in here. So I have circles as one class. And let's say triangle. Red triangle as class. Two. So we have more triangles in here and in here. So the problem here is that, as you see, these two features together can separate these two classes. Let's see. If I have a classifier, then I can say that find this circle and find this radius. Anything inside this radius is class, for example, circle, blue circle, and anything outside this radius is class rectangle. You see, there is this separation here. But the fact is that if we use only one of these features, let's assume we don't have x1 and our measurement is only x2. If we use only x2, then we don't have this axis in here. Let's bring this here. So we will have some rectangle, 1, 2, 3, 4, 5, 6, 7. 7, you see, here I will have 7. And I will have 6 in here. And maybe 6 in here. And finally 7 here. I don't have any measurement for x2. And then circles, as you see, are around here. For example, if this is 5, around 5, I will have circles. As you see, the two classes, in terms of only one feature, have a very high overlap. We cannot find any threshold just for feature 1. And this is true for feature 1 as well. If you don't measure feature 2, and you just measure, for example, weight or length or anything in this specific case, then you will not have any separation. But it's amazing. Two features that are not able to separate the two classes, together, there's a magic. Together, they can separate it. When they put the information together on the table, they can separate it. So let's see in the chat, we have a question, I think. Yeah, together, the emphasis here is that, Terry, the point that I want to emphasize here is that anything that can individually separate two classes is good, okay? If we have a feature, like the length for apple and banana length is good. So we can incorporate it. But the other side, we need to be cautious. Anything that cannot separate doesn't mean that it's a bad feature. Maybe if that feature later combined with another magical feature, they together create a, for example, 100% accuracy of separation or 90% accuracy. Okay, so it's not the case that we, for example, we have 10 features, we ask them individually, can you separate it? If they say yes, go to the game, otherwise you are rejected. No, that otherwise is a little tricky. Maybe that person is not a good single player. For example, it's not a ping pong or table tennis or whatever, or tennis. Maybe if it becomes volleyball, it's a good player. It cannot play, it cannot do wrestling, because when we ask individual features, it's like wrestling. Okay? Can you beat him? Yes, go to the feature set. Otherwise, stay out. No, that person might be a good volleyball player, which means if you pass the ball to him, he will have the spike. Okay? So you see what I mean by these features putting, yes. And these features, as I mentioned, the point that amazes us is that these features individually are nothing. They don't show us any clue that they have some information. Okay, so this is the point that makes them hard to find. Because usually we see the features individually and we test them individually. There is a little way to test them, you know, in combination of the others. Okay. It's sometimes the game is like selecting people for the wrestling or karate, it's easy because you ask people individually compete, and anyone who wins goes to the final list. But when it comes to the let me just volleyball or football or soccer, the player that you are testing might not perform well in a team setting and might outperform other team members if it's in a specific team setting. You know what I mean here? You cannot say he was a bad player. Maybe he was the bad player for that set of other players. But if he had people around him, he could change the game. And this is the same story with the features. Anyone who is a good single player is good. But anyone who is a bad single player might be a good team player. Okay? So this makes the feature selection part a little tricky, because what we usually guess or evaluate is we try to help the algorithm by evaluating the like saying this single feature is useful, this single feature is useful. It's really hard to think of, is this single feature combined with this one useful or not? We usually need to limit ourselves to our guesses that are based on single feature performance. Okay, but still that helps. Okay, so what we usually do is that using the feature selection, we try to bring as much guess as possible. Where's the chat? Yes. No, it's not. It's not, Christopher. So feature selection, so after feature extraction, we usually try, for example, we can go 50% more than what we need to keep. Then feature selection algorithms can be used to select the optimal set of features. And for optimal set of features, still, we will have the same problem there. Are we talking about optimal individual features? That's totally different setting. Or optimal set of features of feature set of 5 features. That might be a different story. Okay, so searching for the optimal set is the topic of feature selection. So how can we, because if we want to go and search all the possible cases, it will be time consuming. Is there any suboptimal search that we know it's not totally 100% optimal, but it's fast enough and optimal enough that can be used in practice? Okay, so this is the topic of feature selection. If we have candidate features after feature extraction, feature selection tries to select some features to be used in the classifier design or eliminate some features from our current set of features. When we do the feature extraction and feature selection, now we have the data available for classifier design. So let's see, we talked about error of the classifier. Error is simply the percentage of the success of the algorithm. Okay, so 95% success is error of 5%. We talked also about the training error and test error. Usually, if you have enough samples, then in these cases, it is like, for example, it is like reading all the possible Java programming books. If someone reads 55 books about Java, he will perform in the exam well, as well, because he has read enough. We have had enough samples. But assuming that we have only 8 sessions to talk about just part of the discussion, then we need to make sure that the performance in the test has a high correlation with the performance in the class. It's not the case that the person learns what we say but doesn't have the ability to add a little creativity to the problem and solve something that has been unseen. Not 100% unseen, but it's a new data. So then here comes the training and test error. If we add more features, usually training error reduces. Training is the error on the examples that we have seen. So that one reduces by incorporating more features and more features. But we don't want to design a smart doctor or intelligent doctor that can only talk about the samples that it has seen before. We want to use it in practice, which means the new patient that will come to this doctor is a patient that has not been seen before. So are we going to trust the doctor if he has a high error on the unseen samples, although he has a good performance on the samples that were given to him? No, because in practice we are talking about samples that were not seen before. So then we need to select enough number of samples, not to just bring any possible information. We need to just focus using, for example, the feature selection will help us to focus more on the important samples, important features, if we don't have enough samples. If we have enough samples, then bring whatever you have into the game. For example, if you have 50,000 measurements, then bring 20 features to your classifier design. But if you have only 50 patients that you have measured, then we don't expect to see a classifier with 20 features. Okay, so there should be this balance between the information that you have and the dimension of the classifier design. So it's like teaching. Okay, if I have enough number of sessions to teach you, then I will add any possible dimensions to my discussion, all the details, all the parts from artificial intelligence. But if I want to just convey this message to you in 7 sessions, then I cannot bring all the details. I need to focus on the important parts. So there should be the balance between the amount of information that I'm giving to you and the dimension of the information that I'm giving. I cannot give you high dimension information in 2 sessions. If I have only 2 sessions, the dimension of the information that I will give you, I will talk about only classifier, feature selection, and feature extraction. Then that's enough, because for 2 sessions, 3 dimensions is enough. But if I have 10 sessions, I will have 5 more dimensions to my topic. You see how this is really related to the real learning process? Okay, everything is clear about this balance that is needed? Great. Also, one term that I forgot to talk to you about is the supervised and unsupervised learning. You might hear this term as well. Supervised learning is the classification is supervised learning. In supervised learning, we have the classes. Okay, it is teaching by examples. Okay, which is the case with classifier design. We give the examples, we supervise the learning process. We tell the algorithm, you were wrong, you were right, wrong, right. Using this wrong and right, we supervise the learning process and help the algorithm to have the highest possible efficiency in answering the questions. unsupervised learning is the cases that we expect the algorithm to identify it is much harder. There is no supervision. If I want to compare unsupervised learning and supervised learning, is like having if I want to teach these two concepts to a baby, I will tell him or her that this is pen and this is phone. And if I show him 10 pens and 10 phones, different phones, I expect to see that in cases that I show him another new pen that he has not seen before, he says, I expect him to say, that was a pen or that was a phone. This is supervised. I'm showing samples, clear samples to him. In unsupervised learning, it is similar to real baby learning. We usually don't directly teach the baby, this was this, this was that. The concepts somehow are constructed in his mind based on seeing different types of objects. First, the baby realizes that I'm seeing two different things. We don't tell him that this is different than this. This toy is different than the other toy. This concept in human learning process happens, that when we see different patterns, we classify them in our mind unintentionally or intentionally, I don't know, but we do it. And later, if we find different labels, we label them. Sometimes we don't find different labels, but we keep them stored without the labels even. But if we see differences, then we try to find patterns without knowing the labels. Okay, so unsupervised learning in our topic becomes clustering. Clustering is where you don't know the labels. You ask the algorithm, go and search to see if you see any pattern of separation there or not. You are not sure. You don't know if you have disease or not. This clustering is usually useful when you are, for example, in cancer. Two groups of examples. One is that you have clear classes and then you want the algorithm to learn if this is cancers or not. In other cases that you have had some measurements from for example, those who have had cancers, but you don't have enough information to go deep into the data to see, is there any subgroup of the people that we can separate in here? Although we know this group is people who have cancer, any kind of separation that we can go and measure deeply or not. So this is the topic of clustering that we will not focus in this class, but I just wanted to make sure that you know the term supervised, which is using examples of classes, and unsupervised. Okay. Any questions about this supervised? Supervised is our discussion. Here, whatever we talk is supervised learning. Classification is supervised learning. Any question? Okay, so now let's go and maybe talk about a real example, and also we might do our first classification today. Okay, so let's see. So I want to download some let me bring this down and go here. So now let's go and classification sample dataset. UCI machine learning has a good set of classification and different actually machine learning problems. So if we go there, you will find different problems, the data set for different problems. Okay, so the data set for different problems. So as you see, for example, annealing, the data set for annealing, Microsoft web data, which is recommender systems. It's let's also use this one as an excuse to discuss recommender systems. Recommender systems all are a class of problems which the outcome that we are going to provide here is recommendation of some products or some items. For example, in Netflix, if you watch some TV series or movies, then you will get some recommendations, and it's very critical issue. I mean, it's very yeah. Amazon is one example. Yes, correct. And imagine in US last year in 2017, I think, out of every $1 spent online, 46 cents was 0.46 was spent on Amazon, which shows it was half of the country's online payment happened in Amazon. So part of this happened because of good recommendations. So imagine if you increase the efficiency of the recommender system in Amazon, not 1%, not 0.1%, 0.001%. Imagine the amount of dollars it will create. If you improve it, it will create more purchases, and if you decrease the efficiency, the system will financially bleed. Okay, so it's a very critical issue. In Netflix recommendation, you have only 4 possible chances of recommendations. If you recommend a good movie, the person will continue watching, and if not, it will not watch, and next month it will cancel the subscription. So many of the cases that we are discussing here, if you translate them to the money that the companies are losing, it's huge amount of money. And that's one of the reasons recently, if you see, there are so many job openings for data scientists. That's not because it's beautiful. That's not because it's everyone wants to be in AI, because it is directly correlated to the financial losses that companies are having, and many of the cases it can be easily prevented with some even basic algorithms. And why is the reason? Because the reason is that the industry has been functioning in the traditional way for like a century, and it has been improving its performance in other areas, in so many other areas, like improving the quality of the product, improving the lifetime of the product. Everything was based on the product and the structure of the company. Now that the web has emerged, now that we have information, now the company that uses that information to improve its business is the one who wins. Okay, so the recommender systems are very important. So for example, here, Microsoft web data, if you click on this, you can read the problem or what is it about. For example, artificial characters, we have classification problem, and audiology. It's a multivariate classification, and let's see how many features. It has 226 samples, and it doesn't have the feature numbers. We don't know the feature numbers. But for this artificial character, the number of features is 7, and we have 6,000 samples. That's good. That's good for a classification problem with just 7 features. 6,000 samples is heaven. Okay, but let's this one. It's 279 features with just 452. It's like me feeding 700 pages book to you in 2 sessions. Okay, it will not result in a good outcome. Here we have audiology again. Auto-MBG. This one is regression. We want to predict the mile per gallon of the cars based on 8 features. We have 39.8 samples, but this is not classification problem because the outcome is continuous. MPG, we don't say this is low MPG or high MPG. Whenever we have this separate classes, this is a classification problem. But with MPG, we have a continuous number, and that's the reason. You see here, it says regression because we have some features, and the outcome is not discrete numbers of high, low, medium, things like this. Okay, it's not a steak, medium, well done, or something. It's like going to the restaurant and saying, I want a steak with this specific measure of, being well done or not. Continuous number, not just 2 words. So regressions are those problems with continuous. The output is continuous, not a separate class. So balance scale, we have classification. I'm not sure. I don't know many of these problems. We need to open the problem and study it. Let's now go to this breast cancer. This one. We have, you see this one? It's good enough. You see we have 10 features and we have 699 samples. Very balanced. It will be a good example, I believe. Let's go here and see what we have in there. So it talks about when the data was donated, 1992, number of web hits, so much 330,000 people have opened this page, and number of instances, 710 attributes. Multivariate and classification. So here is the information about the source of the data, the data set information. We need to read this one carefully. There has been some updates that are covered in here. This is a little important part. If we want to get into the details of this problem, I mean, what was the biology of this problem, then there is a paper, relevant papers. You need to go and read them, which shows how this data set was collected and which natural problem it is modeling. Okay, so in these 2 papers, depending on the area that we want to work on. So here we have feature num is just a sample code number, ID number. It's not a feature. It's just like the barcode of that specific measurement. It's just a number. But features from 2 to 10, these are the measurements. For example, these are biology terms. For example, uniformity of the cell size from 1 to 10 is a number that shows the uniformity of the cell size. Uniformity of the cell shape from 1 to 10 marginal adhesion, 1 to 10. So like nuclei and other bland something. So these are the terms for this specific area. For us that are going to use this example without going into the details of where this data was from and what is the real life meaning of any of these features. Just knowing which one is the feature set, which one are the features, which one is the classes is enough. So here I am assuming that I am sitting besides this scientist as a bioinformatician that is supposed to know just a little bit from, not just supposed to know the biology, but not expert in biology, but his focus is more on the informatics, which is getting the data, analyzing it, and returning it to the biologists. So we don't want to discuss what is, for example, uniformity of the cell size or anything. We will just see them as numbers. And column 11 is the class. Okay, this is our class, which will be 2 for benign cancer and 4 for malignant. So our task is to design a classifier that based on 9 measurements from 2 to 10, 9 measurements, can say if the cancer is benign or malignant. Okay, now let's go to the data folder and also dataset description. Dataset description again discusses the dataset. As you see, sample code number from 2 to 10 is the feature set and 11 is the feature. There are also some missing values as well. Okay, so this is the folder of the data. So breast cancer Wisconsin data, let's open it. Okay, so this is the data. This is actually the data, everything together. There are different ways of representation of data because it has been some groups of measurements. So this set is all the groups together in one place. So what I want to do is that, okay, so let's go to here. I will create, first of all, if I want to create this one here, you see this comma. If you open it with Excel, it will ask you, this is Google Docs. I usually use this Google Doc instead of Excel. There are ways to ask the spreadsheet to consider comma as new column. But what I usually do is that, you see, this is what I have. What I do is that I go here, and this one I see, I place tab in there. It's a tab. Or this one you see, this is a tab. So I copy this, not selected that tab, Control C for selection. Now let's find and replace. Control H. Let's say every comma that you see, replace it with the tab. See, this is a tab. Now, and let's replace all. Now all the numbers are tab separated. Okay, this is Notepad++. I think you can do it in the Notepad as well. So now I'm copying this, and let's now paste them. You see, now I have the numbers in different columns. So this is sample ID. let's just use ID number, and this is x1, and let's bring this one in here. This is x1. Let's go up to here, and this is class. So to make sure we have x1 to x9 and class, let's reduce the size. Now we have them in one place. Okay, let's now use this color as the header. Okay, everything is clear so far? Now we have the data set. We are about to design our first classifier, and we will do it in Excel. And you can see even the simple classifiers can be done in Excel. Okay, now that I have this many numbers and they are sorted by the, are they sorted? No, they are not sorted. Usually what we do, we usually make sure that no specific ordering of data is available. No specific ordering. For example, the one who created this file might go with some group of patients first and then store the rest. So we usually randomize. Let's see what rand functions do we have in here. Okay, between 0 inclusive and 1 exclusive. That's what we want. What we can do, we can simply generate a random number in here. Okay, this is a random number, and let's just decrease the number of zeros. The after decimal point. So, and let me do it in here. Insert lab, RND, random. Why I'm doing this? Because I want to make sure that there is no bias in the ordering of the data. Okay, so I did this. And this one. Now, these are the random numbers. Okay, I generated so many random numbers between 0 and 1 using the rand function in Excel. So equals, you see, equals rand. So now let's sort this column, this entire table based on this column. This way, it will shuffle everything. Correct? So what I'm doing, I'm trying to make sure that there is no bias in the order of data that I have received in the dataset. Clear? So sort it from A to Z or Z to A, it doesn't matter. Let's go from A to Z. Now, as you see, all the numbers, now I have the highest number, which is 0.321, and let's see, did I do it from A to Z? Okay, now why the sort? Let's go from Z to A. I don't understand why this sort. Any idea about? Oh, maybe that's the reason. Okay, I got it. I think you're right, Christopher. So we will do one right in here, and every time that I change it, yes, you're right. So I will copy this and Control Shift V. Now you see I have the number, not the function. I have the number. So now I can delete this one. Now that I have a set of random numbers, so delete cells, delete column. Now let's sort A to Z, for example. Where is the sort now? Okay. Let's see. Okay, now sort by one refresh, it appeared. Okay, sort A to Z. Now it is the case that we wanted. Yeah, thank you, Christopher. It was just doing the rand again after we did the sorting. So now I'm sure that this is sorted. Now what I do is, I have how many samples? I have 700 samples, or 699. So let's cut this part. From here, let's go to 120 of them. So it will be 580 here. Let's cut this, Control X this, and create a new sheet. Here we will have that test data. So I cut it. You see, now I don't have 700 data. I have only 580 samples. Also, let's copy this part, bring this in here. I want to separate this because I will later use this one as unseen data to assess the performance of the classifier. Some of this at least. Okay. Okay, so let's rename this. Let's call this test and test data. Rename test data and rename it to this one, train data. Okay, so now I want to talk about a specific classifier, very simple to calculate classifier, which is k nearest neighbor. The idea of k nearest neighbor, which usually is used in 3 nearest neighbor or 5 nearest neighbor, is this. It says that if you have these two classes, okay, so one is circle and another is star. It says that if you see a question mark, for example, I have a, no, let's use a better color. Question mark. Let's use this color. no, this yellow. So I have a sample, this yellow one. It says that find 3 nearest neighbors to this sample. This yellow, what is the 3 nearest neighbors? It seems that this circle with this circle with this circle will be the 3 nearest neighbors. Okay, 3 nearest neighbors. So it says that if you see the neighbors are circles, then 3 nearest neighbors are circles, then that is circle. Classify that as a circle. Or if you have it here, if you see 3 neighbors are a star, this neighbor, this, and this, then say it is of class star. But if it is in here, then see who are the neighbors. For example, if this is the center, that the point that I'm looking for, 1 is the nearest neighbor, this circle, out of the 3 neighbors, 2 are a star, then say it is a star. Okay, this KNN, K nearest neighbor, K nearest neighbor, usually is used in terms of 3NN, which is 3 nearest neighbors, a neighbor, and 5. These are good enough for many of the cases. So now let's see in our case. I have a data set. Data set means that I don't know the class. Although I know the class, I will not show the class to the algorithm. So what I do is that I go to, let me create 2 copies of this file. Open it again here. So this is my train. So in the train, let's bring one of the data sets, test data sets, up to here. We don't want to show this class number to the algorithm. So I'm just copying x1 to x9, 9 features. Let's bring them here. Okay, this is my test. And to make sure that we are in good column size, let's go this way, x1 to x9. So my question is, what is the class number of this one? What is the class number of this one? Okay, so in k nearest neighbor, what we will do is that we will find the distance between this number, this one that we are looking for, with all the training samples. So to make that one happen, I am copying this actually this many times. What happened? Okay, part of it is in here. Okay, so let's see. Yes, I will go to the Euclidean distance, Terry. Euclidean distance, and we will find the 3 nearest samples to this number. Okay, to make it a little bit more systematic so that we can test other numbers, let me delete this part. What I will do is something a little different. And maybe with this one you can learn a little bit more if you about the Excel. Okay, so I will put the sample that I'm going to find the class in here. This is the sample that I want to find the class. I don't know. I know, but I pretend I don't know. So to find the distance between this one and this one, okay, so it will be equal to this number minus this number. Usually we find squared. Euclidean distance is the one that we usually use. Squared. Okay, so now let's see. D30 minus O2. D3, yes, minus O2. This is correct. It is 1 minus 5, which is 4. Squared will be 16. This one is 1 minus 6, 5 squared, 25. So everything is correct. Agree? So the sum, or which is sum, which is equals this squared, is going to be the sum of these numbers. Okay, we found one. Correct? Any questions here? The first sample had the distance of 231. I mean, distance is squared. If you want to make it correct, it should be square t square root. This one is the actually Euclidean distance. Okay, so now I want to just grab this part and release it in here, but one problem will happen is that then it will find the distance of this row with this one. I want to fix this one, you know, I don't want to, so I want to find the distance of every row in here with this one. So to make sure that when we drag this, it doesn't change the rule, we in Excel we can come in here, and what is the sign? Let's see, what is the suggestion? We use the dollar, exactly. So the part that we don't want to change is this row size. So we put the dollar in there, and to, instead of repeating, so 15.2, I delete this. I first drag this 15.20, the same. Now if I do this formula, okay, this is done. And what happened in here? Control Z. Okay, now I have the distance between, for example, this one, yes, N2, you see, this is N2, C4 minus N2, everything is N2 in this column. Okay, so now I have the distances. Now I should find 3 nearest neighbors. Sort by the last column, exactly. So since I'm looking for nearest neighbors, sort from A to Z. Okay, nearest neighbors. Let's see what happened. The nearest neighbors, if I want to select only 3 nearest neighbors, what are the classes that we see in here? Is it 4? Do you see any 2? Even if we go with 5 nearest neighbors, which will be here, we only see 4. So what is the majority vote on the neighbors? It is 4. So what we say is that all the nearest neighbors, 3 nearest neighbors or 5 nearest neighbors, they were 4. So our decision is to go with 4. So let's see if the classifier worked well. So the class, suggested class, caps lock, is 4. Let's see. Now let's see if we were correct or not. Let's go to test data. It was actually 4. So classifier worked well. Now let's go and test it on this sample. Let's copy this. So this one worked well. I put 1 or true, let's say true. Okay. Let's see this one. Copy this. Paste it in here. Yes, only copy that one row. I have a smart doctor. Okay, just do that measurement, bring that in here, then sort based on this column, and then go with 3 nearest neighbors or 5 nearest neighbors. That's your choice, but be consistent. So 2 nearest neighbors, 3 nearest neighbors. What are the majority of the neighbors? Are 2. So our guess for this one is 2. So let's go to the test data. It was 2. So our guess for second unseen problem, it's taking quiz. Okay, the train data is the book. This one is quiz. So the unseen is true. So our smart doctor so far has correct suggestions. Let's go to this one. Let's see if it will work on this one to make sure that we don't have any problems selecting the numbers. I want to go with painting this one as green. So third one, copy this, go and paste it in here and sort based on this column. What are the neighbors? 3 or 5 neighbors? 2. So actually, let's make this one a little automated. One left. This is the class. This is the suggested class. And our suggestion, our classifier said 4 here, 2 here, and 2 here. So this part we make equals if this equals this one and 1 or 0, let's say. Okay, 1 is true and 0 means false. Let's try 10 and see the accuracy of the classifier. 11, for example. So now let's go with this one. So you see, we have an intelligent algorithm for cancer detection in Excel. So 2, 2, it says 2. It says 2. Let's try one of the 4s. Maybe the detection works well when the class is 2. So let's go to this one. Copy this. Come here. sort A to Z. Wow. So neighbors are 4. But you see, if you go to 4 nearest and 5 nearest neighbors, there is one neighbor which is 2. Okay, if you use 5 nearest neighbors for this specific example, there is one neighbor which is 2. But since it is minority, we go with the majority. 4 of them say this cancer type is of type 4, which has its own name. We just don't want to get into details. So this one. Okay, so far we have the classifier which has the accuracy 100%. But if you try this on all the samples, we don't want to go into the details. Yeah, 3 or 5. You usually decide it. You don't say, okay, now I want to go with 3. Next time I want to go with 5. You go with 3 or 5. Okay, you decide it. Each of them has its own. Yeah, no, it will not happen, Terry, because it's an odd number. So with odd number, there will not be any tie. We don't go with 4NN. We don't go with 6NN. We go with 3 or 5. We can go with 7 as well, but it's not usually the case. 3 or 5. 5 is a little bit smoothing because it's bringing more neighbors into the game. It is good case when you have jitters on the decision boundary. So 5 can help in some cases, and 3 is also good enough in many of the cases. Okay, so this is your 3 nearest neighbor. Now you have your first artificial intelligence project, and nothing anywhere. It's in Excel. You can just plug any new data. It will tell you what type of cancer. And let's go back to the terms about these cancers. One is what are the types of the data here? So benign, which is a good case, and malignant. So with this system, you can identify benign and malignant, and for this one, you can recommend further clinical, procedures. The same. Thank you. Before you go, I'm ending the session, so I just wanted to make this announcement that now that you have your first classifier, you can go to any of the other examples in here and have your first, do the same for a different problem. On UCI machine learning, you see so many different problems in here. Read them, apply them in Excel, or code them in C++ or Java or anything. But the announcement that I want to make is that there is a student conference coming, a student scholars conference. So if you would like, out of the topics that we are covering here, with solving one of these problems in here, you will have good enough project for a poster presentation there. So if you are interested, the conference will be in March. I think there will be good prizes, both as recognition and also a little bit of not scholarship, but I think it will be a good financial prize as well for the winners. And with a good project out of solving one of these problems or combination of these problems, for example, go and solve one of these problems with 3NN in C++ or in Java, code the same. It's a for loop. You need to find a distance and then finally show the result. You can, if you were in my Java class, you can design your GUI. We can enter the numbers, and then that GUI can show us the outcome. It's really easy. You see, anything that can be done in Excel, for sure it can be done in Java. And then we can introduce, in next sessions, we can introduce 2 more algorithms. And you can, so the project, the process is this way. You select 1 or 2 of, or any of these problems, go and read them. So this is step 1. Analyze the data to see what it is about. So let me write the steps so that if you are interested, then I strongly recommend participating in this. The price as well, you can use it to strengthen your resume later for finding jobs or anything. It's a good opportunity. So step 1 is select 1 project or data set. Step 2, read a little bit more, not in details, just a little. Read about the data set, just to know what are, just a little about the data set. And then apply 3NN that we did today, plus maybe next session we will talk about one of the density estimation. They will be easy again. Implementation will be easy. Another plus 1 more algorithm. And then it will be put all the study in one place in a poster. The formula, which one? I will share this file with you so you can see all the formula. Okay, so let me share it now. Let's not postpone it for later. So where is the share? So AI club cancer example 3NN. Okay, so this is AI club, share. Okay, let's go in here. Now get shared link. Anyone can view. So this is the link I'm putting in the chat section. The reason I'm putting this one in a view mode is that no one edits it. But if you don't see the formula by clicking on the tables, then I can change it to the edit mode as well. Where is the chat? It's here. Okay, so any formula that we talked about is in here. Done. So now you will be able to access this file from your browser. So coming back to this announcement, I think it would be a good opportunity to select one of the projects in here. It's since as you saw, it took less than an hour to both download the data, put them in Excel file, even code it, and even after that analyze it. So select one problem. Read about that problem. If you want to present about the cancer, you need to know what is cancer at least, not specific information. And then use 3NN that we did today with 1 more algorithm that we will do next session or other sessions. Compare them, put them in one poster. The event will be on March 13. Okay, so it will be March 13.